Hi and welcome back to this latest video in the series of videos that we're making. So I was wondering what to do for this one, and a friend of mine, my good pal Paul, gave me a couple of chips. He says, what can you do with those? So these are actually PT2399 chips, and these are used in a lot of analog guitar effects for delays, so you can use them as a delay chip. You can use them for choruses, things like that, with a bit of work. And he's given me a couple, and he says, just see what you can come up with. And I thought, okay, I like a challenge, so why not? Let's see what we can do. What most people are doing with these are using them as echo effect, you know, like used for guitars, and you can use them for other things. Basically that tends to be what they get used for, and you can get out of each chip, you can get about something like about a maximum of 300 milliseconds delay. It's not that long, but it's okay for echo effects and things like that. So yeah, let's explore and have some fun with these PT2399 delay ICs and see what we can do. The first thing I did was instantly go on the internet and just see what everybody else is doing. I thought it'd be nice if we could try and make it into a nice chorus effect. I particularly like choruses on guitar. I think it's a great effect. And personally, I have the Boss effect in my pedal board thing that I usually use for my guitar rig. So yeah, I like choruses. Always have done. So I thought it'd be interesting to be able to try and turn one of these into a chorus. Got to start somewhere. I've never tried one of these before, so this is a learning curve for me too. Let's just try and get one to work first, and then maybe later we can progress to some sort of stereo arrangement or whatever. Let's just see how far we get. Okay, so let's have a quick look at the datasheet for the chip. Looks like it's designed by Princeton Technology Corporation. .tw, Taiwan. It says the PT2399 is an echo audio processor IC utilizing CMOS technology, and it has an ADC and it's got a DAC, analog to digital converter, and a digital analog converter. Yeah, so and it's got 44 kilobits of data in there. It also features an internal VCO circuit. You can adjust the VCO frequency, and it talks about its distortion and what have you. So yeah, this is a brief overview of the chip. So this is a block diagram of the chip. This particular datasheet isn't particularly clear in terms of what all of these sections do. They've got op amps, or what looks like operational amplifiers, in here. It's a little bit strange, the labeling on the top is, well, what are you supposed to do with those? So but you can see that it does have a memory block and some sort of clock in, clock out, demodulation, what have you. 44k bits of RAM. Okay. And it's got a VCO on pin 6 there. And that's the pin out. So as you can see, we've got power, which is +5 for this chip on pin 1. The grounds are pins 3 and 4. And just reading around, people say you should connect those both together. There's a clock out on pin 5, which allows you to use that as an output. And it's also handy for checking the clock frequency to see what it is. The VCO control pin is basically just a resistor to ground. It varies the oscillator frequency depending on the resistor that you have. There's a couple of capacitors which connect to pin 7 and pin 8. All of this stuff on the right hand side is those blocks I was just talking about with internal op amps and the output of the D to A and what have you. So not particularly clear, but it has been translated on another web page which I'll link to in a moment. And these are all the pins. So yeah, it does say op out 1. It says, you know, operational amplifier 1, input output. This pin can be used to modulate, demodulate, integrated by connecting the capacitor. So it does give you a sort of a description of what's going on, but it's not that clear, to be honest. And there's a block diagram in echo mode. So if you wanted to use it as a delay, you could basically follow this. You could look at this and it gives you an idea of what's going on. I've got the maximum ratings and what have you. So yeah, it's all 5 volt stuff. Supply range. Here's an application circuit for an echo, which is interesting to see. You'll notice that we've got our 5 volts on pin 1. Pin 2 is just a reference voltage, which isn't actually being used in a normal delay mode, so it's just decoupled to ground. Pin 3 and pin 4 are both going to ground, although there is a subtle difference here. I've noticed they've used a different ground for pin 3 than they have for pin 4, but reading around people say just connect them together, like here. Pin 5 is not used in this particular case, that's actually clock out. Pin 6 is our VCO control resistor, which is this 20k here, which goes to ground. And pin 7 and 8 both got capacitors, which both go to ground. Now all of the right hand side of the chip is basically the output of the DAC, digital analog converter. So analog signal from the delay line is being filtered, if you like, put through various filtering, audio filtering, before it's allowed out. There is, I believe, some sort of feedback here as well going on, where you can mix the signals, and that's probably giving you a certain amount of repeat. I think that's what that 50k is doing there by the looks of it. That's for a delay, surround delay. Interesting. This is important because don't forget, for our chorus pedal, we're trying to get the delay time as short as possible. And yeah, it's a bit difficult to read the chart, but basically it works out that this is the fastest time or fastest clock you can get. This is the slowest, which gives you 342 milliseconds of delay, which is, yeah, it's reasonable for a little chip like this. It's not so bad. As you can see from this, even with a very low resistor on pin 6, the VCO control resistor, 500 ohms. Well, actually, hang on, that is ohms. No, half an ohm. In other words, basically straight to ground. The maximum speed is 31.3. Now, we'll come to this later because we'll actually make a measurement of the circuit and see what we're actually getting. But that is running with a clock of 22 megahertz. So the maximum permissible speed of the clock appears to be, if this chart is correct, it appears to be 22 megahertz. That's about as fast as you can go normally. And that's going to give you 31.3. Okay, so that's interesting. So we're going from 342 milliseconds is the longest, with a clock speed of 2 megahertz, and we're going all the way up to 22 megahertz, which is going to give us 31.3 milliseconds. And you got your usual pinouts and dimensions and what have you. So that's all very good. Now there is another website, and I'll take you there right now, called Electrosmash. Electrosmash have gone ahead and have done a very good job at going into a lot more detail than what's on the official sheet, and they've obviously done a lot of work to get this to this kind of detail, almost like reverse engineering, I would imagine. There's the same block diagram there, but you'll notice they've got this now, which gives a much better idea of what the internals of the chip are doing. Those are those op amps that we're looking at earlier, and you can see now how they're actually connect to various sections. And there's our pin 6, if you can see that. Pin 6, and it is the control for the VCO. There's also a little bit about the power supply there, and probably internal biasing and what have you. But the important thing is the delay line. So you've got signals coming in, you've got signals coming out, and a modulator and a demodulator, and basically that'll be like a DAC. So as that comes out, then it goes through some sort of a demodulator low pass filter, it says there, and out we go. So that's a much better explanation of what's actually going on inside of the chip, better than the official documentation, to be honest. And there's a 5-volt regulator to get it going. A little bit about the internal grounds, which interestingly has a 10 ohm resistance inside between the two grounds. Okay, and then you've got like 2.5, which is V mid, really, isn't it? Between 5. So that's all internal. An anti-latch up circuit connects to pin 6. What happens is there's a problem with the chip where if the VCO control resistor is too small in value, roughly less than 1k, then the chip can have a tendency to lock up when you first put the power on. So they recommend that you keep the resistance higher than 1k or whatever it is. It's written in the sheet somewhere to make it reliable on switch on. And if you want to go lower than that, like we do for a chorus, you can use an anti-lockup. A little bit of a delay when you first turn on the power, before pin 6 is taken to ground. So yeah, it says here that when the frequencies of the oscillator are the maximum of 22 megahertz, the delay time is 31.3. Yeah, it's just what we were talking about earlier there. So that appears to be the maximum. But there's a pin 2 hack where you can take pin 6 down to ground, which gives the minimum delay. And it says here, perfect for chorus. Look at that. Perfect for chorus. Interesting. So maybe there is a way to do this. Access to the internal. Yeah, so they're saying modulate the reference input rather than trying to modulate the VCO. That's showing the output of the clock with the while it's being modulated. Yeah, okay. And there's our table again. And they're saying basically what that's the same table more or less as what they've got on the data sheet by the looks of it. That's about as far as we're going to go on here, but I just wanted to point out a few functions of the chip. They appear to be quite cheap. You can pick up these chips for about £2.50 here in the UK, something like that. They're not expensive, and well, they give you a delay, and they can potentially give you a chorus. Okay, so the first thing I wanted to do was take a look on the internet and see what other people are doing in order to make chorus pedals from the PT2399. And one of the first things I came across was this design, which is basically the Little Angel mini chorus, designed here by Rick Holt, August 2010. Thanks to Rick Holt for this one. We're just looking on the internet here. There's two basic approaches to doing the chorus circuit that I can come up with, that I can think of just reading around. One is to modulate pin 2, which is the reference voltage pin of the 2399. So modulating the reference as shown here in the Little Angel design here. And the other way to do it is to modulate pin 6, the VCO control current. So there's two methods that I've found looking around on the internet, and I want to try both of them and just see which one's best. What we're aiming for, if you remember, is a low delay time, something in the order of 20 to 30 milliseconds thereabouts would be ideal for a nice chorus sound. But we also want a nice rich deep modulation as well. We're looking at this now, this circuit here now, and as you can see, this is the LFO here. It's generating a very slow sine wave or thereabouts. It may be triangular, not too sure about that, but the output of this is going through a depth control here to vary the amplitude of the signal, and that is modulating, varying in amplitude, the reference voltage of pin 2, which by the way is normally fixed internally in the chip at 2.5 volts as a V mid reference from 5 volts. So it's normally at 2.5 volts. So this is actually going to force it to go up and down a bit, and that's how you get your modulation. That's neat. The other advantage with this circuit is you'll notice pin 6 is through a 100 ohm resistor to ground. That means it's going to be driving maximum current to the VCO control circuit. The VCO control circuit is current controlled, so the higher the current, the shorter the delay time. The lower the current, the higher the delay time. So the fact that this has got 100 ohms in is pretty much as low as you can go with this chip. It means we're driving maximum current for the shortest possible delay time. That should actually give us around about 30 to 32 milliseconds of delay, which should be okay as a chorus. So yeah, that's how they're doing it here. And I want to build this or something very similar to this. It may not be exactly the same, but I want to see how much depth we're getting from varying the pin 2 reference voltage. So that's one method. Let's go and have a look at another method where we modulate pin 6 instead. So here we are at the Valve Wizard page here, and this particular design is called a Jenny Greenteeth. That's a great name. Jenny Greenteeth, weird chorus it says, pitch bend ring modulation. Oh, interesting. The thing to notice here is that this is our LFO down here producing a triangular wave. Just like before, goes through a depth control to vary the amplitude of that. By the way, the LFO is running around about anywhere between 0.5 of a hertz to like 1.5 hertz. You know, around about 1 hertz worth of signal, but of course it's variable. There's a 220k rate control here for the speed. So you were kind of in the 1 Hz range from about half a hertz up to 1.5 hertz. Through the depth control, you'll notice there's a couple of transistors on the bottom, and a bit more about this in a moment. I'll get into that later. But basically, as you can see, this signal here, which is the LFO inject signal, this actually is modulating pin 6. And you will also notice that pin 2 on this particular design, which is the reference voltage, and in the other design, in the little angel, that was being modulated by the LFO, is now just decoupled to ground by a 47 microfarad capacitor. So the internal reference is not being adjusted in this particular circuit. And as I say, these are the two methods that, looking around on the internet, seems to be the only real two ways you can do it. I haven't found any other methods. So the choice is yours. But I want to try and build this one as well. The Jenny Greenteeth weird chorus. I like the sound of that. Sounds like fun. Let's just see what kind of a delay time we can get this down to. The reason for modulating pin 2 in the other design and not pin 6 is because pin 6 can be taken straight down to ground for maximum current, which means that you can actually get the delay time as short as possible. And I think that was the idea of modulating the reference rather than modulating the VCO current. This design does it the other way, leaves the reference alone and modulates the VCO current instead with this BC337 on the bottom. This lower transistor is actually the current modulation, if you like. The upper transistor is to do with the latch-up protection circuit. And one thing that needs to be pointed out, I may have mentioned this earlier on when we looked at the website datasheet. If you have too much current flowing through pin 6, when you first power up the whole circuit, you have a problem with the chip locking up or latching up, if you like. It's just a peculiarity of the chip that you have to be mindful of when you're designing circuits. They recommend nothing less than about 1K. If you have a kilo ohm resistance down to ground, it should probably turn on every single time. But if it's less than that, then you can expect latch-up condition. So this top transistor is basically a initial turn-on delay, and that's what this 47 microfarad capacitor is doing with this diode and this 100K to positive 5. And it is basically, it's a bit like a reset circuit going to a microcontroller. On switch on, the capacitor is discharged at 0, and it takes time, because of the time constant of the 100K and the 47 microfarad, for the signal to rise up to 5 volts from ground. That turns on this top transistor, another BC337. Once that's on, it allows the current to flow. Basically, it's a timed switch. Think of it that way. And that gives us maximum current. So then the other transistor can start modulating the current to pin 6. That's what the double transistor arrangement's doing. One's a time switch, the other one is the modulation transistor. The other part of this particular diagram is the filtering of the chip, which is the output of the demodulator, DAC, from all of that. And these circuits are almost identical. There's a couple of small changes between capacitance values, that kind of thing, between this and the little angel design. But roughly, everybody's kind of doing it the same way with a few component changes. So I'm just going to copy what everybody else is doing. I don't need to reinvent the wheel. A lot of people have put time into this and I don't want to. So why don't I just copy what other people are doing for the audio side, and we can just concentrate on what it actually sounds like, comparing the pin 2 modulation to the pin 6 modulation techniques. So that's what we're going to do. I hope that explains what the rest of the video is going to be about. We're going to build 2 circuits, we're going to compare them, take some measurements and see what they sound like. And hopefully at the very end we'll get the guitar plugged in and we'll actually have a listen. That would be nice. Right, so here we are in Kicad, and as you can see, I've entered in a schematic diagram of what we're going to build. Again, I'll say it again, this is for modulating pin 2 as opposed to modulating pin 6. What we have got here, this is very much like the little angel design, and I've just basically entered it in to Kicad for clarity. So yes, this is our LFO circuit down here using the LM324. That's the way we're going to do it. This has got a speed control here, we've got a depth control here, and this signal, this amplitude from here, the amplitude of the LFO here is going to be adjusted by VR1 and injected through R11 here into the reference input pin, which gives us our modulation. You'll notice pin 6 in our case here is basically through a 100 ohm resistor down to ground, and we've got this BC549 which is acting as the anti-lockup. Right hand side of the circuit, or the right hand side of the chip of the PT2399, is all audio filtering and signal conditioning, if you like, from the input through the op amp to the output. It's mixed and filtered. That'll be the output of the demodulator and the DAC, what have you, within the chip. And this audio signal is being mixed with the clean signal coming through to the output jack to the amplifier. So this is what we're going to build. This is our first version, and we're using pin 2 as the modulation, as we said, and we're going to use pin 6 purely to set the highest possible clock frequency using this 100 ohms resistor here, and this anti-lock is purely to stop the chip from locking up when you first switch it on. So let's go in and build this on a bit of board, and let's go and check it out, see what it's like. Let's go. Let's make a start. Solder some pins here. I think I've mentioned it in another video that I really like this board. It's very cheap off eBay. I think it was something like a couple of pound and you get 10 boards or something. It was something like that. It was not expensive. It really comes in handy for prototyping, you know. I used it on the if you look at the repeater video that we did, the early version, it was done on the same board. So I use this quite a lot. Now this is obviously through hole work here. I'm not going to be doing any surface mount on this particular project, but of course it could be. You could always, you know, go ahead and once you've got the prototype done, you could, you know, make the whole thing surface mount. The main thing is that we can prototype very easily with this board, you know. We can do through hole projects and surface mount, which is wonderful. Or a mixture of the two, even. You could actually use a, you know, this through hole chip and surround it with surface mount components. Nothing wrong with that. There you go. I'll just wipe the tip. There you go. Those are now on. Okay, so I'm just going to bat on. We'll add some more components and I'll be right back. Okay, so a little bit of an update. This is how far we've got. I've got the chip holders on. We've put on the 5-volt regulator, the 78L05. A couple of decoupling capacitors. Got that onto a little battery clip here. So first thing I'm going to try is just see if we've got 5 volts before I go any further. This all, first of all, let's check our battery. What's our, I think this is a bit worn out, this battery. Yeah, 7.5. It's supposed to be 9 obviously, but it'll do for the test. So that's 7.5 volts from this semi worn out battery here, and let's just put that on and let's measure the output of the regulator. Where are we? I think I've got a bad probe or something. Ugh. Do I need new probes here? There you go. And there's our 5 volts. Change range. 4.979. That's close enough. So yeah. So the input voltage is that 7.3 from our half worn out battery, and the output is 4.98 volts. So yeah, looking good. That's our 5 volts rail up and running to drive the delay chip. The 9 volts goes directly, you know, the battery raw 9 volts goes directly to the op amps, and that's already, I've got the power already connected there. So let's keep going. 5 volts is good. Let's keep it up. Okay, so next progress report, put some more components onto the board. We're looking at this section here, which is the LFO. We've got that wired up and populated on the board. You'll notice I've got the LM324 in, but not the delay chip yet, haven't got that far. So that's as far as we've got. You'll notice I've got a scope probe on here, and I'm looking at the output of the LFO, and we're powered up off the 9-volt battery. So let's go and have a look at the scope and see what we've got going on. We're monitoring the output of the LFO, let's connect the battery and see what we get. Hey, look at that. And it seems to be, it's oscillating, and it's pretty low frequency. The output is about 1 volt peak to peak. I'm just going to try and alter the potentiometer for the speed. Yeah, looking good. Let's just turn the time base up a little bit. Might have been better if I put this on the storage scope, but I think you can probably make out it's kind of a sine wave. So that's the LFO working. So that's a great start. Okay, let's progress. So this LFO is actually going to be modulating the clock frequency of the delay chip. There is another control that we need to add for depth, which is basically the amount of this signal we inject into the reference pin of the delay chip, which in turn alters the clock frequency. And that's what gives us our chorus. So yeah, we've got an LFO working. That's a great start. Okay, so after a little bit of effort, we have now got a fully populated board, the delay IC here, and we've got our LM324 quad op amps here. All the other components have been populated as per the diagram. So it's kind of done, and underneath it always looks a bit of a mess. Bit of wiring going on, but it's simply to prove the point, to prove the circuit, whether it's actually any good or not. So let me plug in a guitar, and I've got my amplifier here, Psychic 15 here, Fender practice combo, and we've got some jack leads plugged into the board, got some jack connections here, and it's all a bit sort of thrown together. I haven't even got a proper, what's it, the depth control is on a preset at the moment, and this is the speed control. So yeah, it's all a bit thrown together. Anyway, let's plug the guitar in and see what happens, see what it sounds like. Let's put the battery on. Got the guitar here, and let's just see what it sounds like, huh? Oh, I heard a click. That's a good start. Aha, right. Well, it's got some sort of modulation going on. Well, it's got quite a nice sound, but it's not very chorusy. Usually harmonics, you can hear them on harmonics. You can kind of hear it, you can hear it modulating, but I don't know. But it does have a modulation. Okay, let's have an adjustment. Hang on. Yeah, you can hear it there. It can go faster. Yeah, let's try the depth control, which is a tiny little preset. Slow it down a bit. I don't know. Not convinced. Not convinced it's any good. Yeah, it's kind of like pretty, I don't know, not very chorusy, a little bit chorusy. You can hear the modulation going. And that's maximum depth as well. That's right up there. I would have expected that to be a lot more deeper, you know, more modulation going on. It's quite mild, really. There's not a lot going on. Speed it up again. I mean, that's quite interesting, but not really chorusy. Yeah, well, interesting sound, but it's slow it down. I mean, choruses are usually quite slow, like, you know, like a sort of a, almost like a Leslie speaker turning around sort of speed. And at that speed, you can hardly hear the effect. Okay, so conclusion so far, well, at least it's a working circuit. It's actually modulating. It's given us, you can hear the delay time, but the delay time is quite short. So maybe we can measure the delay time. That would be interesting. If you remember on the diagram, we've got the pin 6, which is the VCO input, or VCO control, I should say, which normally goes through something like a 1 or 2K resistor, typically, to ground. Well, on this particular design, it's only 100 ohms, and that goes through this transistor to stop the chip locking up when you first put the power on. And that's all working. I've already checked that with a scope, and it does indeed go up and down when, you know, when you first switch it on, so it's fine. But we are getting a modulation, but the modulation is not very deep, which is coming from the LFO inject, and I've got this to minimum resistance. I've got that turned right up, and so this output should be able to really modulate this quite a lot, and we're just not really hearing a lot of variation. At least I'm not here with my little combo here, little cheap practice amp and the old trusty guitar. So it's not exactly let's say a professional setup, but you should still be able to hear the modulation clearly, and I'm not really hearing that. So I think there's more work to do here. So I'm going to stop the video for a moment and do a bit of a jump cut. I'm going to go away and have a think about it. But I'm glad we got this far. I've already gone through it and checked my work a couple of times just to make sure I haven't actually made a mistake, and it is correct to the diagram. Let's try measuring the delay time that we're getting from this chip. Remember, it's set pretty much to its minimum delay. Let's see what we've actually got. So what I'm doing is I'm just putting in a square wave right now at 10 Hertz. So it's just a, you know, a very pretty low frequency square wave. So we can look at the rise and falling edges on the storage scope, and we can take a measurement, compare the input falling edge to the output edge, either negative or positive depending on the phase. So let's have a look at the storage scope screen from our 10 Hertz signal and see what we're actually getting. Okay, so I hope you can see the screen. I'm finding it difficult to get my camera any closer. What we can see on the top trace is the input falling edge. We want to compare that to the amount of delay time that we're getting. And we want to measure the amount of delay from the input signal to the output. This is the output here, this blip here. So let's try and measure this this distance. So let me go to the cursors here, and we can move the left-right cursor here, and I'm going to line that up to the input. Let's have a look. There you go. Now we need to set the cursor to the output, just there. Get it right at the peak, and now we can actually take a measurement and read it from the screen, and it's saying it's 25.2 milliseconds. So we're actually getting 25.2. We'll do that measurement again, make sure everything's correct. There's the falling edge. Yeah, 25.2 milliseconds. Let's try the other side. Let's try the rising edge. Should theoretically be the same. Let's have a look at that. It's less than ideal. I don't have a lot of room in the workshop. We are limited. Okay, let's get the bottom trace measured there. That's it, just there. And yeah, 25.4 as opposed to 25.2. Yeah, it's pretty much the same. It could just be down to the resolution of the screen. There you go, 25.2. So 25.2 milliseconds delay that we're getting, and that's running, I do believe, at pretty much at its maximum speed. I don't think we can get that any shorter. So the next thing we can probably do, now that we know what the delay time is that we're getting, let's have a look at the actual clock frequency, which we can measure from one of the output pins on the delay chip. It does actually have a clock output pin. So let's measure that and see what frequency we're getting. Let's see if this all makes sense. So here we are at the frequency counter, ready to go. Pin 5 of the delay chip. Pin 5 is clock out, so we should be able to measure the clock frequency of the chip. Let's do that right now. Let's have a look. Right, we're on there. That's on there now. 27.5, 27.6. There's a bit of variation for whatever reason. Maybe it's because it's still being modulated a little bit by the LFO. But that is megahertz. Let me double check. Yeah. 27.5, 27.6 megahertz. That's a pretty high clock frequency. And I've got a feeling we are not going to get this to go any faster than that. Probably right at its limit. Now I do have 2 of these chips, so what would be interesting is if I change the chips, let's see if it's any different. Let's do that right now. Turn the power off. And this is the probe I'm using onto pin 5. Let's just remove that chip there. And let's try the other one. Yeah, it's just interesting, you know, we're experimenting here. Little bit of a, you know, play around just to see if there's any differences between the chips at all. Possibly the characteristics are slightly different. Making sure the chip is in the correct way around. And I'll reconnect the battery and we'll go and have a look. We'll go and have a look at the frequency counter again, see what that's doing. Okay, so I'm just putting on the battery now. Battery is on, and I'm going to put the scope probe back onto pin 5, clock output, and what do we get? Oh, well, what do you know? Look at that. Pretty much 20 megahertz. Shall we say 20? 19.92 or something? 19.9. Almost 20 megahertz. So there's actually a difference between the chips. Who knew? It's probably because it's not in its guaranteed operating area anymore. You know, we're pushing the chip to its limit. We're trying to make it go as fast as possible. And I'll just double check that, and we'll switch it back to the other chip just to see what it's like. Let's try that. Okay, so the chip's been changed, and I'm putting the power back on. And let's put the probe back onto pin 5. What do we get? And there you go, back to 27.9 again. Nearly 28 megahertz almost. So there's a difference of almost 8 megahertz. That's quite a lot between the 2 chips. That's quite an inconsistency, really. Whether we're outside of the guaranteed limit or not, that's quite a difference. That's been interesting. I'll just come back to the board here. So that's been an interesting test. As I say, these 2 chips, that's our probe that was going to pin 5. Battery's off. Take the chip out. I should really mark this, shouldn't I? I should actually put a little mark on this one. Let me just try and put a little mark on here. Yeah, I've put a tiny little mark on the chip. That's the quickest, if you like. Highest clock speed. So yeah, we've got 2 of these chips, and I'm looking at them now, and they're absolutely identical in every way. So there's something very strange going on. Something very strange going on with these chips. I'm reading the numbers and they're absolutely identical. Can't see that on camera, of course, too small. But you get the idea. So, so the other thing was there was a lack of, if you like, modulation going on. It wasn't particularly deep until you turned the speed control very high. I'm not really convinced how far we're going to get with this. It's, you know, I didn't really like the sound that we were getting from the thing. I may just leave it right here. I don't want to call it a fail video, although it probably is. But if you're more familiar with this design, the little angel chorus, please do comment. Dive in. Tell us what I'm doing wrong. Do I need to change these capacitors to mylar polyester? I don't think that's going to make any difference, or enough difference. Maybe it's a little bit of difference to the total quality at the end of the day, but it's not going to give us a deeper It's not going to give us a deeper modulation, and it's not going to give us a shorter delay time, that's for sure. There's got to be something maybe I've done wrong. If I've made an obvious mistake, maybe we'll come back to it, we'll fix that and do another video, whatever. Okay, so I've gone ahead and put together pretty much our final design. At least this is a simulation of the modulation side of the chorus. I'm not showing the actual chip or any of the audio filtering or any of the audio amplification going in and out. We're just looking at pin 6, which as you know is the VCO pin, and pin 2, which is the reference 2.5 from the chip. And what I've decided is to modulate pin 6 because of the findings that we got from modulating pin 2 and the depth problems that we had. And I've put it into symmetric simulator on purpose just so we can actually run a simulation without having to build everything all the time and see what it's going to look like. Here's our LFO modulation coming in. I've got it set for 300 millihertz at the moment, which is a bit short. I think we'll take this up to about 500. That's half a hertz. That's 0.5 of a hertz, 500 millihertz. And we're going to modulate through this voltage to current converter circuit, which is basically an op-amp, LM324 in our case. We're going to have a bit of negative feedback from the voltage which is developed across R1 here, which is 100 ohms. This is going to give us a better linearity and control of the current from an input voltage, rather than just like trying to feed it straight into the base, which you can do, but I found this method to be better. Current limiting onto the base of Q1. I'm using 2N2222 transistors as opposed to the Jenny Greenteeth design. This is very similar to the Jenny Greenteeth design, as you'll see, except for maybe this being added here. And also we now have this delay control, which actually alters the delay range of the PT2399. So we can set the quiescent current by adjusting the voltage into the positive input here. We can adjust the quiescent current through this chain here up to pin 6, which is controlling the VCO frequency inside the chip. We also have, just like the other designs, we also have Q2 here, which is pretty much the same, which is delaying the turn-on current from the initial switch on with the battery. This particular circuit is going to give us around about 100 milliseconds thereabouts. But what I have done is decreased the value of the pull-up resistor to the capacitor which has to charge. I've changed the time constant a little bit, but not so much the time constant. I've tried to keep that relatively the same as before. But the point is that now we have more base current by reducing this value from, it was I think about 100k or 150k, I've reduced it down to 56k. And what that's done by making these alterations is, and it's been driven from a 5-volt rail of course, is Q2 is now being switched on harder, which means that you now have a lower on resistance between the CA junction, and that allows us to get more current flowing, because what was happening in the original design when I tried it, we weren't really getting the, it worked, but we weren't really getting as much depth as we could have been. And when you actually measured the current, I discovered that it was because Q2 wasn't really being turned on hard enough to get the maximum current to flow, which, as you know, gives us the lowest time delay. If you want to get up to 6 milliamps, which is pretty much as high as the chip can operate at, if you try to squeeze any more current out of that, it will actually go up to 8 milliamps if you do a dead short and have nothing in line. You can get 8 milliamps. But the difference between 6 milliamps and 8 milliamps is negligible. There's hardly any difference in the actual VCO frequency change. So there's no point in going any higher than 6 really. By making that change and changing the 56k and making it lower, more base current, which in turn gives us more through current through the whole circuit to VCO. And that allowed us to get another milliamp or two. It was fairly, it was very noticeable, which means we can really squeeze that delay down as good as we can. Q1 was acting all right already because it's actually being controlled by the op-amp. It was able to swing current as far as the transistor could handle, but Q2 was not being turned on fully, or fully enough, which is strange if you think about it. By changing the values of the latch-up circuit, it's altered the sound from the chorus because the VCO current can now go higher. So this is our simulation. The other thing to note is, you notice pin 2, 2.5 reference. This comes from the chip, And normally this would just be decoupled straight to ground with a capacitor like a 47 microfarad. We're actually using that as a voltage reference, so we're actually using pin 2 as an output, and we're tapping into that and using it as our bias, if you like, or quiescent current resistor chain here, which has got a variable in the middle, which allows us to set the quiescent point of the voltage to driving Q1, which in turn allows us to alter the current to pin 6. In effect, this control through all of this is altering the current in the chain, which is great because it means we can turn it maximum and minimum. You should be able to get the delay to go to about 340 milliseconds when it's at its minimum current, and at its highest current we should be somewhere in the region of 32 milliseconds, maybe even less. So that's what we're actually doing here, and the idea here, as I said in this little box here, is set for the shortest delay with the best chorus modulation swing. You have to use your ears at this point and what sounds the best. So, but it's allowing us to alter this quiescent point. So let's run the simulation and just see what it looks like. I'll click run. You'll notice the VR1 trimmer is at the moment set to 50% in the middle of its travel. And you'll notice we are modulating sine wave here from the LFO, and we're around about the 3 milliamp point, kind of in the middle. It's a little bit less than 3 milliamp, it's about 2.9, 2.8-ish. So yeah, that's where we are. So we're modulating positive of that and negative of that. This is an increase of current here, and this is a decrease in current here along the center point there, which would be the whatever we set this to. So let's have a look at the modulation again, but this time we'll turn up the resistance to say 90%. Now what do we have here? You notice the current has increased. We're now roughly in the middle here, which is about 5.1 milliamps, and we're going positive and negative of 5.1 milliamps. Well, for a chorus that's better because the current is higher. Before it was 3 down here somewhere, now it's like 5, and that means we're going to get a shorter delay. So this is really taking the chip to its limit, almost. We're almost, where are we at the top? 5.7 it says. When we look at the datum being displayed at the bottom here, when I go to there, it says 5.7 milliamps. Can we go any higher? Let's keep going, let's try 95%. I've changed that to 95%. Ooh, there you go, we're hitting 6. So we've got 6 milliamps at the top, and on the bottom we've got 5 milliamps, which is very convenient. You'll notice that's 6 at the peak and 5 milliamps at the trough. So we've got exactly 1 milliamps worth of modulation swing going on from the LFO. Very nice. That's probably spot on for a chorus. Anyway, we'll go to 100%. Run that again. Okay, we're over 6 now, so we're like 6.28 at the peak, and we're 5.3 at the bottom. So what happens is we're pushing it further than what the chip will probably react to. So what we would hear would be the modulation probably clipping, and in other words, not really doing anything, like a dead spot. That's what I think will happen when we come to build this for real. I think there'll be a point where you adjust the point of the trimmer and you'll get to the point where the VCO just doesn't react anymore. So you'd probably have to back that back this current back a little bit, this potentiometer back a little bit, and get the current down. So that's pushing it to its upper limit. Let's push it to its minimum limit. I'll take this right down to 0. This is now 0% of its travel. Yeah, now the scale's changed a little bit, so it looks a bit funny, but just bear with it. We're now in microamps here, not milliamps anymore. So that's half of a milliamp. Yeah, 500 microamps over 500, maybe 600 there. 550, I think it is there. But you'll notice the bottom, it bottoms out at a current which is actually negative. It's actually going negative currents. So this is going far too far down, which means we may have to have altered the value of our 6 here. Might have to just change that value so it doesn't go as low as this. Our minimum is roughly around about 80, 90, something like that microamps. If we change this to say, I don't know, let's try it. Let's try 100 ohm. I don't want to mess with these values too much, but let's just try 100 ohm. See what that looks like. Yeah, it's still too high. So I don't know, 220. What is that? What's 220 doing? Yeah, it's still clipping. So you'd really have to adjust these values for a while. I'm not going to spend too much time in the video doing that. Do that off camera. But basically, we can get this. So the idea is that the top peaks hit 6, and the bottoms basically get down to about 50 microamps. We're just too high. I'll try 1K. What the hell? Give that a go. Where are we? There we go. So now it's not clipping, and the bottom is 78 microamps, which is great. 78's perfect. That's going to take us below where we need to be. Let's just let's try the top 100% travel again. And this is what Symmetrics is really good for, because you can do things like this. This has given us a maximum of 6.6, so that's probably too high. We don't really need to go that high in terms of current. So we could adjust R5, and you know, you could actually get your calculator out if you want to do this properly. I'm a bit lazy. I'm just messing with values and see where it comes out. If you want to get it exact, you can sit with a calculator and you can actually figure out the total current, and you can work out, transposing the formula of the resistances and everything. You can get it so the voltages are correct, you know, the correct amount of swing. But perfectly honestly, it takes seconds just to change values. We can bring this down to, say, we want to decrease this, don't we? Bring it down. Let's try 47K and just run that again. What's our upper limit? The 5.1, so we'll want to be less than that. So I want to be more current than that. 47. Let's try 39K. It's kind of in the middle of where we were. I think this should be somewhere near. There you go. So now we've got just touching 6 milliamp. It's about 5.9. That's lovely. And down to 5. So it's 5 to 5.94-ish. So there's our top modulation. And we'll just see, because we've altered this, it's probably affected this. So let's try the the 0 again. And you can do this and spend as much time as you like messing with values. This has taken us down to 10. If you look at the datum at the bottom, 10 microamps, which is further than we needed to go, but it's absolutely fine. Right, so, and it's not going negative, which is good. You know, you'll notice actually this settles down to about 35 microamps. So yeah, that's actually pretty good. So there's our, I'll just save that. There's our final design for that. That's going to give us a maximum and a minimum set point. We're going to adjust this for the best sounding chorus we can get, and hopefully that's still got a low delay because we're turning on Q2 a bit better than what we were. And we've got this voltage to current converter circuit here, which is hopefully going to control Q1 a bit more linear and a bit more under control from our quiescent point. So that's it. Let's go away, and I'll probably end up putting it into Kicad just to tidy it up with all the rest of the information that we have, the rest of the schematic that we have from the filtering side and the power supply and everything for the PT2399. We'll add this in, end up with a schematic that we can actually build on a board and try. So let's do that now. Okay, so here we are in Kicad, and I've gone ahead and entered in the changes that we've made from our version 1, if you like, from the modulated reference pin version, rather like the very similar to the Little Angel design. And here we've gone ahead and entered the components from the symmetric simulation that we came up with, and we are now modulating VCO current, much more like the Jenny Green Teeth design. I've changed the value for the pull-up resistor for the anti-lockup circuit. We've changed this to 56K from 100, and we've increased the capacitor to 10 microfarad to try and keep the time constant the same, but at the same time, as we mentioned in the simulation, I won't go through it all again, but we've decreased the value of this resistor here to turn on the transistor more, which means we get a bit more current flow. I've added in this part of the circuit, which is the voltage to current translation, or converter if you like, which is controlling this bottom transistor, which is in turn modulating the current to the pin 6 of the VCO. We've also put in the values that we determined for the upper and lower range. That's like 6 milliamps maximum current, round about 90 microamps for the lowest current. This gets us in the range that we want. You'll notice this has also been driven from pin 2, which is the reference output, 2.5 volts that will be. It is decoupled with this 47 microfarad, and that drives the top of the potential divider here. Okay, you will notice that we don't have an LFO yet. It's decoupled by 4.7 microfarad, but we don't actually have the circuit actually entered into Kicad yet, and that's because I wanted to try this on the bench first using the function generator. So it's easy to adjust the frequency just by turning a knob on the front of the generator, and we can also select different waveforms. In particular, I'm interested in going between sine wave modulation and triangular wave, so we can check that out and see what it actually sounds like at the end of the day, which one's best. So rather than commit to a circuit, I thought, no, we'll put it on the function generator and we'll just see what it sounds like first, and then we can design something around what we want, that way around. So this is the voltage to current translation, all of these parts here, which we explained earlier, and this is the anti-latch-up circuit, and that's kind of it. All of the output side of all of the right-hand side of the PT2399 is exactly the same. We're using the same components for filtering, from audio mixing here as well. This is the input jack here, going through an op-amp with a certain amount of gain, coming through an op-amp here, and that's been mixed with the output of the, which I think is more or less pin 14 if I'm not mistaken, is the bulk of the output, and that is actually going to the, being mixed if you like, dry signal and affected signal to the output jack, which then goes to the amp. That is the entire circuit. This is probably our final design. It simulates well, at least all this bottom part of it does anyway, and we can now put this onto a board and build it for real, and hopefully we'll get a guitar plugged in and we'll see what it sounds like. So let's get back the bench and let's do that. What I've done is I've gone ahead and constructed this second part of the circuit, which I hope you can see here. You'll notice we've got 3 chips here, and that's because I haven't integrated everything into one chip yet for the LM324. So I've actually got 2 separate LM324s, which is wasteful, but it was just to get the thing working. Eventually these will be integrated into one chip, like we're seeing in the diagram there. So this is the anti-lockup section here, just underneath these probes here. This is now linked into the PT2399 delay chip, pretty much with the existing circuit that we had before. This cable here is coming from the function generator, and at the moment it's set for about 800 Hertz sine wave. So we're putting in I'm just glancing across there to the function generator, 872 Hertz, and I've got this plugged into my little Fender combo like we did before. So everything's very similar to what we had before. Let's give it a go, and I've got my Fender Strat here. I've changed guitars from last time. Let's put this on. That sounds good. It went click. Let's give it a go. Well, listen to that. That's absolutely beautiful. Lovely. The well, I haven't even adjusted anything yet. That's so that's perfect. So I'll turn the volume down in case it's too loud. Okay. Very nice. That's a really thick chorus. Now let's have a listen to the delay time that we've got at the moment. So I'm just going to hit the strings on the guitar and just like hit a mute note. It's good. I reckon we've got something like about 30 or 40 milliseconds. Okay. This is the quiescent control. Let's have a play with that. So let's turn it all the way down one way. The delay is now very short. I reckon that's 30 milliseconds. We'll probably be at the limit, so that's correct. Let's have a listen to it. There's hardly any modulation, very little modulation going on. I'd probably have to increase the signal from the modulation signal from the function generator. It could be that it's clamped all the way and it just can't modulate now. So let's increase this. There, it's starting now, I can hear it now. It's almost flangey. Not quite flange, but something like that. That's actually quite nice, but it's not really very deep. Doesn't have a deep sound. So let's increase the delay time by reducing the current in the chain. So let's turn this up. Okay, a bit more. That's a lot nicer. Now it's much richer. That's actually really nice. I could live with that. Yeah, pretty good. Let's check out the delay time just by listening to muted strings again. It's quick. That's perfectly fine. Let's increase this longer. Let's make the delay longer. Yeah, you can hear the delay, it's getting longer. Still quite quick. Ooh, now if you'll notice, the pitch is now getting like wobbly. It's become more than a chorus now. It's starting to bend the notes too much. Let's keep going. Don't know how far we can go with this. Ooh. Ooh, that's pretty wobbly. Let's have a listen to the delay time. Yeah, I think we're up to probably about 100 milliseconds now or something. Let's keep going. I don't know how far I can go. What may happen is if we go too far, it might start basically hearing the, you might start hearing the sample rate and everything. We'll see how far it goes. It's getting longer. Some of them's really long when the LFO goes right down the bottom. And of course the modulation's now crazy. And if you want a completely crazy pedal, well, there you are. Sounds like a broken tape deck. Or one of those loop copycat tapes with a with a bad connection, with a bad tape joint. Let's keep going. Okay, let's go crazy. Oh, there we go. Hear that? That's actually hitting the sample rate. Now when the wave goes through the point now, it's starting to actually distort, or let's see what it sounds like anyway. Yeah, it's crazy. Unusable. Okay, we've gone too far. Come back a bit. Let it settle down. That input capacitor from the LFO, it may be a little bit too big. When you adjust the quiescent control, it's taken a long time for it to settle down. You probably want it to react faster, so might have to reduce that to say 2.2 or 4.7 microfarad. Still too big. But let's have a listen to the delay. So you hear sometimes it's very long. Depending, there was a long one. If I hope you can hear that. Tick-tock. That's probably about 200 milliseconds. Or maybe it's even 300 milliseconds. Sometimes, depending on where you are on the, on the LFO curve, on the LFO current control, sometimes you'll get a shorter delay, other times you'll get a longer delay, just depending on where you catch it. That was a short one. That was a long one. Yeah. That's crazy. So that's obviously too long and unusable unless you want a special effect for a crazy track. Let's reduce this. I'm going to sort of put it in the middle. I don't know, put it in the middle. Let's have a listen to the delay. Pretty good. That's short. 30-40 milliseconds perhaps, without measuring it. Sounds lovely. Okay, make it a bit longer. I'm just playing around here, having fun. That's nice. It's quite a thick, deep chorus sound now. Yep, that's nice. So I think we've actually succeeded in what we wanted to do. We've built a chorus from a PT2399 and we've managed to modify some of the circuits that's already out there, as fine as they are, but we've managed to get the current higher to the VCO pin, which has given us 30-40 milliseconds chorus delay time, and we'll get a nice rich thick chorus sound because of the modulation. So really that's it. That's pretty much what I was aiming to do. It would have been nice to get the delay time even shorter, but I'm quite happy with the sound we're getting from around about 30 milliseconds. So it gives a nice rich sound. The only thing is there is a little bit of a slap back, but I can live with that. I mean, that gives my Boss chorus pedal, you know, commercially available pedal, it gives it, you know, a run for its money. That's comparable to the sound that I would get from my Boss, I think. I would have to A-B them two on the bench, but pretty happy with that. So really the only thing we'll have to do to finish the project would be to add an LFO. I already know a good modulation frequency. As I say, it's about 850 millihertz or 0.8 of a hertz thereabouts, and you can adjust that and play with that. The only thing we need to do now is measure what sort of modulation amplitude we've got. So let's put that on the scope and have a look at the amplitude of the LFO. Let's do that right now. So I'm feeding the LFO into the storage scope here. It's better than using the analog scope because it's such a low frequency you can't really get a reading on the analog scope unless you just look at the top and bottom points. It's easier to see here. And what we're seeing is, obviously it's a triangular wave. A little bit of noise in here probably because of the way I've got the earths connected here. But the important thing is that it's triangular, which sounds pretty good. It sounded nice earlier there. And the amplitude is important. So looking at this, we've got 50 millivolts per division. So that's 50, 100, 150. It's just over 150 millivolts peak to peak, more like 160 or so peak to peak. So that's the kind of amplitude that we're looking for after adjustment from the LFO. We can put it through a control, which will give us a depth control, how much modulation you send to the voltage to current converter. So we can make a depth control just by altering this level. But this is the sort of the nice range, shall we say. We'll probably want to go positive and negative of that signal level. The only thing left to do is to compare the sound from the signal generator and compare this to a sine wave. So we can click between sine wave and triangular and just see what it sounds like. So let's give that a try. We know the amplitude now for the sort of modulation that we want, plus or minus of that. It's about 160 or so millivolts peak to peak, and then we'll take it from there. Right, so here we are back again. This is with triangular modulation, as I say, about 160 millivolts peak to peak coming through these red-black connections here. That's our LFO. Explained all that earlier. So let's just have a listen to a few simple chords. listen to that for a moment. Let's try some harmonics. It's quite nice. Now let me switch over to sine wave. Okay, I've just switched over to sine wave there. That's nice too. Lovely harmonics. So both are good. Let's increase the delay time. You'll also hear a more deep modulation. Let's check out the delay. Still pretty quick, that's acceptable. Okay, let's go back to triangular. Just triangular. I think with the triangular you're getting a constant shift because it's a ramp up, then there's no hanging about, and then it's a ramp down again. You're constantly getting a shift of pitch, whereas with the sine wave you're getting a change as the sine curve goes up, and then at the top, at the peak, there's not a lot of modulation going on for a while, and then it starts to come down again to the trough, and that's another modulation, and then when it gets to the bottom of the trough there's not much modulation. So you're kind of getting modulation, no modulation, then modulation, and you can hear that. Whereas with the triangular it's constant, it's like a constant shift, which I think is probably nicer. So I can't decide. I think they both sound fine. Maybe in the final design we need a little switch so you can flick between sine wave or triangular. That will make the LFO circuitry a bit more complex, but whatever, if that's what it takes. Sorry about any distortion you might be hearing. Like I said, it's actually very clean here sitting. It sounds great. I just hope this microphone isn't distorting. Okay, right. So in summary, I think we've achieved what we wanted to achieve. The only thing I would need to do is to build the LFO, get all this into Kicad, and finish the schematic. And I might do that in another video. I think for now, I'm gonna say success. Let's call it a success video, even though at the very beginning we thought it might have been a fail video. This sounds way better than what we had when we started. And it's took quite a few iterations of component changes and, you know, just trying to get the whole thing to sound correct. I hope you've got something from this. We may do a part 2. Comment below what you think, if you'd like to see us actually finish this. We could even put this on a PCB if you really like that. If you would like me to do that, we can put this onto a PCB and get the thing in a box. I don't know, put some funky graphics on it. That seems to be what people do these days with with foot pedals. There's some crazy pedals out there, isn't there? And all sorts of weird graphics and things. So we could go that far, but that sort of gets away from the electronic side as far as I'm concerned. This is sort of like as far as I'm going to go with this video, and I think basically we've proved the point. Yes, it can definitely be done with a PT2399. There are diagrams on the internet already for various designs. We're not really making anything brand new here. I've just simply taken existing circuitry that was out there on the internet, and perhaps we've made it a bit better, by reducing the delay time. And to my ears, you know, I've been playing a while and I've tried different choruses. This is actually very nice sitting here with this little practice amp, and it's a nice chorus. So that could go in a box, and there you are, you've got a foot pedal. So I hope you've got something from all of this. Do comment below if you think I'm completely doing it wrong. Let me know, whatever. I'd be interested to know what your thoughts are. But I'm sitting here, I'm playing the guitar, it sounds nice, and I think once I stop the video I might just play a little bit more and maybe try some different delay times and what have you. And there you go. So yeah, it's a toss-up between triangular or sine wave modulation. Both sound good to me. Maybe there's a switch so we can flick between the two, something like that. And there you go. Thanks very much for watching, and I hope you got something from the video. And do comment, and don't forget to subscribe if you like this kind of thing, and give us a like. That helps the YouTube algorithm and all that nonsense. So very best luck, and thank you again for watching. See you next time. Bye bye.